So, Assalamu alaikum wa rahmatullahi wa barakatuh. Okay, can you all hear me? All right, good. Okay, so I have 8 participants now. 7 out of 14. Yeah, out of 14, because on my list 14 have registered. Okay, some are joining now. Let's see. Now I will share the syllabus, which I will upload also later on the Blackboard. I will briefly go over it. Please, I hope you can hear me clearly. If you have any issue, with the sound, please let me know so that I can from my end. Okay. So can you see the syllabus? Okay. So I will just, like I said, I will upload it. So as usual, in the syllabus, as you can see, it has my phone number. That is the office phone number, which you can always get me. It has my email address, which if there is any issue, you can contact me via the email. And then it has my office hours. Although you will not be coming physically, but during the office hours, I will be available on Blackboard, on my email, so that if you have any issue, any concern, you can call via phone, my landline, on my office telephone, or you can chat me up on WhatsApp. Okay, that's if I'm available on WhatsApp at the time. But most importantly, I'll be available on Blackboard and via email to respond to anything that you may have. Okay, and the course has lab. I will also take the lab with you. We're supposed to start the lab today. But this is week 1. Most of you are having issues with your registration, fixing 1 or 2 things. So for that, we will begin to take the lab next week. Okay, so be ready next week to come, not in your thobe, the lab dress. You have to wear a trouser and a shirt. Okay, you using thobe, gutra, igal, all are not allowed. Okay, so you have to come kitted. Okay, so we will start next week. Okay. And then we'll start on time at 2. Okay, and that is physical, so meaning you have to come to the campus. And then for the reference textbook, okay, yeah, I am enlarging the and for the reference textbook, you have the it's already written, Hydrology and Hydraulic Systems by Ram Gupta. 4th edition is available in the library, so you can go and borrow it. Okay, you can go and borrow it. Yeah, these are the course objectives, which you can go through. Let me go to the second page. The course objectives, the course outcomes, the mapping, okay, and then the chapters to be covered. If you look at the course, it's really a very heavy course. It has, I think, 16 or 17 chapters in the book, and we are to go over. It has up to 15 or so. So, and basically, it compresses hydrology and hydraulics. Okay, so it is a very heavy course which will introduce you to hydrology and hydraulics, or in general the water engineering aspect. Okay, so it's a very heavy course, but we will be introducing you to the basic concepts under each chapter. Okay, we will not go so deep. Okay, we'll introduce you to the basic concepts under each chapter, and then we will leave the rest for anyone that may be interested in taking his option electives at the senior level in water engineering. For instance, the same course is like broken into about 3 or 4, about 4 courses, you know, at the senior level. So you have many courses, you know, that you can go and take, you know, where you will be introduced to the deeper treatment of topics under the course. Okay, you can see here. So this is it. Let me go to the next page. Okay, so attendance in class, you all know, I think most of you took fluid mechanics with me, you know the rules, you know, for attendance. You need to be available, although this is going to be online, the lecture while the lab is going to be on site. So for the online as well, you need to be available before the start of the class, which is on Monday at 11. You should be there. If you are late by more than 5 minutes, you will be marked as absent, okay? And for the lab, you should be available at 2 exactly, because we are going to start at 2 exactly, okay? And then, of course, the DN policy, you have 1 in 1. If you have 3 absences, 1 in 2, 5 absences, DN is 7. Without excuse, with excuse, you have DN to be 10. And for the lab, when you miss 1 lab is 1 in 1, 2 labs, 1 in 2, 3 labs is DN, okay? And with excuse, you have up to 4 labs. So you are all, you know, matured enough now not to just be absent like that, okay? So I hope nobody will have DN in the course. And when assignment is given, okay, if you have any excuse, you should for not attending a class, so you should get authorization from the excuse committee, okay, from the college excuse committee. There is an excuse committee chaired by, although Dr. Slayer is not here, but you can, I think Shiraz is part of the committee where you can present your medical excuse or whatever it is for them to issue official excuse that you are to present to your instructor, okay? And this has to be done and presented to the instructor not later than 2 days following resumption of class attendance, okay? So if you miss a class, when you resume the class, you have to ensure that you submit that excuse within 2 days. Otherwise, it may not be considered. And cheating, plagiarism, you'll be given homework, you will do term project, you know, which is lab-based, okay? Cheating is not allowed. And as we are going to see, I always discourage students from copying homework, you know, copying lab reports, copying, you know, in the term project. Now we introduce something called assessment, in which we will verify, you know, it has a weightage, as we are going to see in the assessment plan. It has 5%. The assessment simply means I will just ask you questions about a homework that you submitted and even did well. I mean, how did you do it? If you cannot defend it, it means you did not do it, and you will not get the points for under that assessment. I can pick your lab report and ask you questions. I can pick your term project report and ask you questions. So if you cannot defend it, it means you just copied from someone without knowing what you copied. Like I always say, it is not a crime for you to go and learn something from someone who you think knows better than you do, but it is a crime when you just copy without knowing anything, or just copy verbatim, copy everything as the other person has written it down. You have to learn. That is the most important thing. This is engineering. It is not social science, okay? You have to know what you are doing. You have to learn the basic concepts, understand them, and be able to apply them, okay? So this is very, very important. Now, penalties for violation of academic integrity, of course, you can get 0, you can get F, okay? All this, if you are found wanting, you can get F. I mean, the grade on the assessment can be reduced if it is established that you have really cheated, okay? All this can happen. And then lab rules, we all know the lab rules, okay? Now you will come in with your face masks, and then we'll provide hand sanitizers in the lab, and we'll provide hand gloves, okay? And then social distancing will also be established. Assignments and quizzes. As usual, we will take, for every 2 weeks, we will have a quiz, and for every 3 weeks, we will have an assignment, okay? And this is also in the weekly schedule, as we are going to see, okay? And okay, so this is the schedule of classes for week 1, okay? What we're supposed to do. Let me move to the next page. I hope you can hear me clearly. Okay, good. All right. So this is the weekly schedule, not the dates for the major exams. Major 1 is going to be held week 6. So start preparing now. And you have to ensure that you don't have any conflict with other courses, which we tried as much as possible to avoid that, okay? So check your other schedules and ensure that you have no conflict, okay? Don't come when it is, I mean, during like week 5 or week 6 to say, no, I have conflict with so-so course. Check all the syllabi, check all of them, check the major exam dates now, and ensure you have no conflict. Okay, of course, when forming this schedule, we ensure that there is no conflict with with general courses and what have you. So check to ensure that you have no conflict. It is your responsibility, not ours. And don't come week 5 or 4 to say I have conflict, because then it may be too late. Okay. And like I always say, start reading from now. You don't wait until week 5 or 6 when the major is around the corner before you start reading. Our major 1 is going to be week 6 on Sunday at 6 to 8, okay? And it's going to cover this first 4 chapters, okay? And major midterm lab is week 9, okay? During the lab hours, and major 2 is going to be week 11, okay? Major 2 is going to be week 11. I hope, let me check. Yeah, on major, okay, Sunday. So I hope nobody is taking EE 211. Because it has been scheduled the same time with EE 211. Okay, so I hope nobody is taking EE 211 electric circuits. Is anybody taking electric circuits? Okay, so now and then the final lab is going to be on 15 during the lab hour. Now the next. Okay, this is the major exam schedules. Okay, so check, like I always say, please check your other courses and ensure that you have no conflict. If you have any conflict, report to the instructor ahead of time. Report now. Don't wait until it is week 4, 5, or 6 that you will realize that you have any conflict, and then you will begin to run helter-skelter here and there. Okay, check all the syllabi and ensure that you have no conflict. Make a calendar for all your major exams. Okay, make a calendar for all your major exams. And I think what will happen, I will also create a WhatsApp group for the class. Okay, so that that may give, I mean, it may enhance our communication. Okay, although really nowadays I normally keep my phone in the office, so it's active during the working hours. When I go home, it may not be there, but the WhatsApp group may be, I mean, a very good way to communicate. Now, the assessment policy, like I told you, you have something called assessment, which is 5%. Okay, I explained this 5%. It will verify. We have one fluid mechanics. No, fluid mechanics is not the same time with water engineering. Fluid mechanics is the following day. Fluid mechanics is on Monday. I will be the one to be taking the fluid mechanics. Oh, Okay, one for fluid mechanics. Okay, then I will check and see if all the members are also the same members for the water engineering. Otherwise, we may need to update. Those that are not taking the water engineering, we remove them, and then those that are currently that did not take the fluid mechanics with us, but they are with us now, we will now add them. Okay. Now for the assessment, like I said, the assessment will basically check and ensure. Oh, let me pen so that you can, yeah. Okay, pen. Okay. So the assessment will basically ensure that homework, lab reports, term project. Yeah, these three will ensure that these things you did not just go and copy from your friend. So I will ask you questions from the homework that you submitted. I can ask you to how to solve it, or what are the steps, or whatever on your lab reports, and ask you based on the questions that you submitted. Okay, and the same thing with the term project. So these are ways to verify that you really did it, you don't just copy. And if if you answer all the questions correctly, you get your full points, 5 points. Okay. If you don't, you get 0 for that. Okay. So I'm still urging you to, if it is homework, make sure you do it, you know how to do it. You learn how to do it, not just go online to copy and just, submit just to get the points. You have to know how to do it, because if you don't, that will affect you in your first major exams, in your, first major, second major, and final, because these are more or less, the questions revolve around your quizzes, your homework, and what have you. So if you don't know, how the homework was solved, then you will definitely land in trouble. Okay. Of course, now you are big guys, so you are more matured. So I'm expecting that you, really take your time to learn it. And the course, like, it's not something that is very difficult. It's not difficult at all. It's a very interesting course that I hope you will all enjoy it. Very interesting one. Now, done with the syllabus. Any question about the syllabus? Okay, if we don't have any question about the syllabus, like I said, I will upload it on Blackboard. Term project will be individual. Oh, it's going to be in group. It's going to be in group. You will be grouped, maybe 2 or 3 groups depending on the availability of instrument and what have you. So there will be group. But then again, your assessment, there's group assessment, there is individual assessment. Because for the term project, there is defense. You present the term project, where I will ask each of the members specific questions that if they fail to answer me correctly, they will not get the points for the defense in that case. Okay, then there will be grades, for the report, and everything. And so that is it. Because it is group, it doesn't mean just one member of the group will do everything. No, there will be question and answer, the presentation of the term project, in which I will ask each member of the group specific questions. And if he doesn't answer the questions correctly, he will fail for he will not get the marks allocated for answering those questions. Okay. So any other question about the syllabus? Oh, I made mistake. I wrote in the something I wrote CE 233. I will go and edit it. It's supposed to be 335. Sorry. It's because I'm also the one to take the fluid mechanics, so the two course codes got mixed up in my brain. Any other question with respect to this? Okay, now we can start. And again, one very important thing, you need to be with your pen and paper and calculator. For all those that took course with me, I give a lot of questions. I ask a lot of questions in which you need to work out some numerical problems, and then we now brainstorm about the solution and what you. So make sure beside you, get pen and paper and a calculator. Okay, get your pen and paper and also a calculator, okay? Because we are going to start the real work now. All right, let's move on. I will share the presentation with you. Also upload after the class on Blackboard for you to have a copy. I'm trying to zoom it to reduce the size. Okay. All right. So this is CE 335, Water Engineering. Okay, and this is the first lecture. And for those that maybe are taking a course with me for the first time, no, we don't have lab. I explained that. Given that this is the first week, most of you are trying to finish your registration and what have you, so we'll postpone it. Next week we start our lab. Okay. My name is Dr. Salih Lukman, and I will be the one to take you through the course Water Engineering. Now, the first topic, the first thing we're going to learn here, we have hydrology versus hydraulics, water resources, assessment of demand, municipal requirements, population forecasting, and design capacity. Okay, and the intended learning outcomes, that is, if you finish taking these slides, what are the deliverables? What are you expected to have learned at the end? Okay, so that's the intended learning outcome. So at the end of the class, or at the end of delivering these slides, you should be able to explain hydrology and hydraulics, explain different water uses, perform short-term population estimation, and determine the design capacity for different components of a water supply project. So these are the learning outcomes. Now, we will begin with a short quiz, a reading quiz, okay? The subject of hydrology deals with what? The subject of hydrology deals with what? Who can attempt? A, B, C, or D? So just type your answer and I can see it. The subject of hydrology deals with A, precipitation, B, rainfall runoff relationship, C, circulation of water and its constituents through the hydrologic cycle, D, groundwater flow. So what is the correct answer here? Zaid al-Shamri, Mihnad, is it Mihnad or Mihnad? How do you pronounce the name? Is it Mihnad? Mihnad Zaid al-Shamri said C. Okay. What about the remaining guys? There are 12 remaining guys. Type your answer quickly. Type your answers. Ahmad Harun Hassan. Munahad. Oh, Munahad. Muhannad. Okay. Oh, so it seems all of you are going for C. Okay. Then the answer is C. Yes, hydrology. The subject of hydrology deals with circulation of water and its constituents throughout the hydrologic cycle. This we are going to expatiate more. The reading quiz is like trying to give you like an appetizer also. So it's like trying to give you like an appetizer, okay, into what you are going to learn in the subsequent slides, okay. So and also to gauge your understanding of what it entails. Of course, even if you get it wrong, it doesn't matter, because in the subsequent slides we are going to explain in details what hydrology is. Okay, and the second question says dash is the study of the mechanical properties of liquids, in bracket water, in physical systems. A, Newtonian mechanics. B, statics. C, fluid mechanics. And D, hydraulics. So what is the answer to this? Yeah, type your answers. Fluid mechanics, D, D, hydraulics. Or some are saying C, fluid mechanics. Dash is of the mechanical properties of liquids in physical systems. Okay, basically the answer here is D, which is hydraulics. But then those that are saying fluid mechanics is like the introductory part of hydraulics. Fluid mechanics and hydraulics, they go hand in hand, okay? You start with fluid mechanics because the fluid mechanics involves statics and dynamics, okay? And hydraulics is more or less about going in deep or into the application of the mechanical properties of liquids in physical systems. Okay, so it's more or less like an extension or an advancement of fluid mechanics. Okay. Now, what is hydrology and hydraulics? You know, we just saw in the reading quiz, okay, hydrology. Hydro means water, logy means study. Okay, so study of water, simple. Hydro from Latin is a Latin word. Hydro, anywhere you hear the word hydro, it means it refers to water. Anywhere you hear the word logy, study. Okay, so study of the movement, distribution, and quality of water on Earth and other planets. Not only Earth, because you know recently on other planets they are still trying to find if there is any evidence of life on the Mars. I think recently, I think probably they found water, because if you find water, then it means there is life, because that is the basic element, I mean, that tells you about the existence or otherwise of any life. Okay, so hydrology is the study of the movement, distribution, and quality of water on Earth and other planets, including the hydrologic cycle, water resources and environmental watershed sustainability. Okay, movement. Okay, this we are all going to explain further. When rain falls on ground, it moves through gutters, channels. Okay, it joins the rivers join the oceans, like that. Okay, so that's the movement and the distribution. How is it distributed? Some of the water soaks into the ground to join the groundwater flow, isn't it? And the quality of water on Earth, you know, you have the fresh water, the sea water, which is salty, and you have all different types of water with different qualities. Okay, and the hydrologic cycle, this will explain in, I think, chapter 2. What is the hydrologic cycle? It's simply the way and manner in which water is distributed in different phases. Okay, from rainfall, that is precipitation, down to runoff, down to ocean, to evaporation, to transpiration, and then you have precipitation again. Okay, so this is like the summary of what the hydrologic cycle is all about. But like I said, we are going to expatiate more on that in the next chapter. Okay, and then hydraulics deals with the mechanical properties of liquids, that is water, in physical systems and how they flow from one point to the next. Okay, so it deals mostly with flow and flow property of water. Okay, and then of course hydraulics or hydraulic system. This is for civil engineering. In mechanical, I mean, you can refer to also hydraulic system, which have to do with the use of fluid. Okay, to transmit energy. Okay, like the hydraulic pump, you know, machine, you know, how our brake works. Okay, this will explain. No, this we did in fluid mechanics. Okay, this we did in fluid mechanics. It is used to evaluate flow in rivers, streams, storm drain networks, water aqueducts. Aqueducts is just pipe, water pipes. Okay, aqueducts, water lines, sewers, etc. Sewers are also pipes, but they carry wastewater. Okay, sewers are also pipelines, but they carry only wastewater. Okay, so we call them sewers. Okay, so the evaluation of flows in such system, rivers, pipeline, sewers. Okay, all this is under hydraulics. Is it clear? Okay. Like water engineering. What do you want to say, Hamdan? You said D, like, is it D? Are you referring to the previous? Oh, like water engineering. Okay. Okay, clear. All right. Oh, you are referring to the reading quiz. Okay. Now the next slide. Feel free to ask any question, please. Feel free to ask any question. If there is anything not clear, feel free to ask. Okay. Yeah, you can see this. Reducing its size because you can see that it has overshoots. So, all right, now development of water resources. Okay, development activity here includes striking a balance. I mean, what do we mean by water resources development? Okay, here is simply striking balance between available water resources and demand for water in an optimal way, which is simply, water resources planning. Okay, you have a town, let's say a new town, let's say an outskirt, let's say Kaisuma is a new town, and we want to, I mean, all new towns, they need utilities like power, road networks, healthcare, and also water, which is life. Okay, so how do we supply water to such towns? Okay, so we need to strike a balance. We need to know what is the population in that town and what is their water usage. That is their water demand. How much water do they need? And then we look at our source. Where can we go and get this water to meet the water demand for this community? Is that clear? That is the available water resources. Do we have like a river? Do we have groundwater wells that we are going to be pumping? Okay, do we need a treatment plant where the water is going to be treated and then distributed to the household? Do we need to dig boreholes for each household? Or what is exactly the available water resources? So at the end, you need to strike a balance between the available water resources and the water demand for the community. That is to ensure that the water resources will be able to meet the water demand of the community. Imagine you need, let's say, 10 gallons or 50 gallons per day, and then you are supplied with 10 gallons. Definitely, that will not meet up your water needs, isn't it? If your water supply is less than your water demand, then definitely there is problem. So for any water resources development, we need to strike a balance between the available water resources and the demand for water. Okay. That's why under the water resources, now under the water resources development, we have two components here, which I'm going to explain in details. We have the quantitative component and the qualitative component. Whenever you hear the word quantitative, it means it involves numbers, quantitative. While qualitative, it means it involves like the quality of or the state of something. While the quantitative, it refers to the numerical state. Okay, so water resource development, the quantitative part here, like I explained in the available water resources, how much water is needed, what is the current and future requirements. That is the current and future water needs. All population, all towns, they expand, they grow, the population increases, isn't it? Hafrul in 2014, I came to Hafrul in 2014. Now you have many structures springing up, many buildings, many institutions. So the population of Hafrul has increased from 2014 to now. That is when we're now 2020. Okay, so population keeps on increasing more often than not, and if population increases, definitely the requirement for water for area for that town will also increase. Is that clear? And then again, we have to look at how much water is available. Okay, by how much water is available, we need to look at the sources of water. Is it a surface water or groundwater? Estimates using principles of hydrology. Okay, surface water here refers to water on the surface, like rivers, streams, lakes, ocean. Okay, all these are surface water. And then groundwater, you need to dig, you need to go in Saudi Arabia here to get to groundwater. You need to dig sometimes on the about 1 kilometer that is 1,000 meters below the earth surface, okay, to get to groundwater. So usually the water level, the groundwater level is usually low. Okay, so you need to dig very deep to get to groundwater, and then you need to estimate these sources, the groundwater and the surface water, depending on which one you intend to use. You need to estimate their quantity. When you estimate their quantity, that is when you can look at the water demand of the community. Is the quantity going to meet the water demand of this community? If yes, then you move on. If no, then you have to explore other sources of meeting the water demand of the community. Because just imagine, per day, let's say you need to drink 2 liters of water, and then you are provided with only half liter. Definitely you will go thirsty, isn't it? Because you need 2 liters normally to function effectively, and then because water is scarce, water is not there, you are provided with just half liter. Half liter, that is 25% of your water requirement, water demand. So that spells trouble, isn't it? That is problematic. Okay. Now, again, you need to explore how are the requirements satisfied by the supplies. Just striking balance between the available water resources and the demand for water. Okay. So how are the requirements satisfied by the supplies? Supplies here, depending on which one, depending on your source, okay? Is it surface water or groundwater? Like here, is it run-off river versus storage projects? Run-off river, that is, well, river is flowing. Unfortunately, in Saudi Arabia, you don't have rivers at all, okay? But you have ocean, okay? Oceans are surrounding, at the coastal areas, the Dammam, Jeddah, in which we use these oceans. We use the water in the ocean to remove the salt and then use the water, treat it for drinking, okay? In fact, most of the water supplies you have, is through desalination. The water demand, okay, for consumption, okay, for municipal consumption, 50% of the water comes from what is called the seawater desalination. Salinate means, salt. So desalination, removal of salt, because seawater is salty. So you have like huge desalination plants. Saudi Arabia has the largest desalination plants in the world. It has the largest desalination plants in the world. And desalination starts in Kuwait, I think somewhere in the 50s or so. Desalination in the world started in Kuwait, but currently Saudi Arabia has the largest desalination plants in the world. Okay, so the main source of water for municipal supplies, the water you drink, you bathe, you do all sorts of things. Here in Saudi Arabia, there are basically 2 sources. You have groundwater obtained from wells, okay, from deep wells, and then you have, from ocean, from the seawater desalination, okay. Of course, the pumping of groundwater, just like pumping of oil. So pumping of groundwater leads to what is called salinating the groundwater. It becomes salty sometimes, even the groundwater. Okay, and because sometimes for the coastal areas you have what is called upconing, okay, or seawater intrusion. This we are going to learn in about this chapter 6 or 7, seawater intrusion, whereby because of the extent of pumping the groundwater, the seawater is now coming in to maintain the balance, to maintain the equilibrium. Okay, this we will explain later in about chapter 6 or so, okay, in this course. Okay, and then how is the used up water disposed of? That's a drainage system. That when you take bath, when you shower, when you wash your clothes, when you wash your car, that is the used up water. How is it disposed of? How do you get rid of that water? Okay, it has to go to drainage system and then to the treatment plant. Okay, so that brings us to drainage system. So all these things we are going to learn in this course, even the design of drains, channel design and what have you. So these are the components that make up the quantitative part of water resources development. Now we will move to the other part, which is the qualitative part. Any question before we move on? Here I saw Muhammad Bashar saying groundwater, surface water. So what do you want to say? If you want to talk, you can talk, okay? Your audio is enabled. So if you want to talk, if you have any question that you want to talk, you can always talk, okay? So now, still on the water resources development, is the water like environmental engineering? What do you mean by is water like environmental engineering? Water and environmental engineering, they go hand in hand, as we are going to see here. The qualitative part is having to do with environmental engineering. Let me present this slide and then I will come back to your question. Okay, so for water resources development, I explain quantitative part having to do with the the quantity, the source of water, and then how do we dispose of the used up water. Okay, now for the qualitative part, it deals with the quality of water. What type of water is needed? I mean, what is the quality? Do we just go to the ocean and get the water and just pump to the household? No, the quality is very bad because that of the ocean, it is salty. It needs to be treated. And that tells us what kind of water as well. I mean, is it water from ocean? I mean, is it water from ocean, from rivers, from lakes? What treatment is required? Okay, because once we ascertain the quality of the water, then that will tell us, okay, do we need to treat it before distributing? Okay. What do you mean, Muhammad? That is standard for it? Like I said, you can always talk. Your audio is enabled. So if you want, you can always talk. Okay. What treatment is required? What is the quality of the wastewater discharged? In the previous part for the quantity, where we were talking about drainage, and then here we are talking about the quality of the discharged wastewater. The mic not available. Oh, the mic not available? Oh, then it means, okay, let me check the settings quickly. Session settings, audio, video settings. Buttons, share audio. Okay. All right. So I think now the mic is enabled, I think. Yeah. I enabled the mic now. So what is the quality of the wastewater discharge, and what are the effects of the wastewater discharge into a river? A river which is having, relatively good quality water. When you discharge wastewater of, too bad quality, it will affect the aquatic life, because in rivers you normally have aquatic life, fish, and other organisms are found in the rivers. Okay, if the water quality is too bad, it can change the quality of the river to such an extent that the aquatic life will be endangered. So all these are having to do with the qualitative part. Okay, so you can see the link between water resources and environmental engineering. The water resources part, sorry, the qualitative part deals with water resources engineering, which is having to do with the quantitation of flow, the quantity of flow needed, the source, and what have you. And then the quality part is having to do with now, okay, what is the quality of the supplied water and the wastewater to be discharged? Of what quality is it? Okay, so that is the environmental part. And that is why water resources and environmental engineering, they usually go hand in hand. Okay, they usually go together. Is that clear? Now, demand for water supply. Okay, I already started explaining the demand for water supply. Here I will explain some specific things. Withdrawal uses. Okay, we use water. This involves diversion of surface water or groundwater for irrigation or water supply. Okay, when you take out water from any source, okay, either surface or groundwater for irrigation or water supply. This is withdrawal uses, and we have non-withdrawal uses. Non-withdrawal uses, it means we use the water in place, in situ. Okay, we use it in situ, that's in place. Involve on-site uses such as navigation. Navigation here, just providing pathway for, boats, for ships to navigate, to move around, okay, on the water. And for recreation, you have the Cornish, okay, where you just go and relax and look at large bodies of water, and then just take some refreshment and enjoy the scenery. So these are non-withdrawal uses because you just go by the side of the ocean and just watch, okay, and that's it. And then you have the consumptive uses. The consumptive uses here refers to withdrawn quantity that is no longer available for further use. That is, it is water you withdraw, similar to one. But then, like in irrigation, when you just pour water on the crops, and then the water some will sink to form the groundwater flow, and some will will run down the channels. Okay, but then some of the water will be used up by the crops. Like when you use water to bath, you don't take anything. The same quantity goes, whatever, if you are using 10 liters, the same quantity of water you start with, you end up, the same quantity of wastewater, you will generate the same quantity of wastewater. But what about the water you drink? Yes, when you take, let's say, half liter, when you drink half liter, you may urinate, let's say 0.3 or 0.4 liter, but part of the water will be used by your body. It will be used by your body, in providing, in ensuring that the cells are functioning well, in this and that, such that that water will not be available, will not be excreted. Of course, most of the water, you either urinate or you sweat. So all these are coming from the water that you take in. But there is small amount, which is about 10 to 20%, that will not be released back. Okay? You cannot release it back. Okay? So this is the consumptive uses. Okay? So very small, 10 to 20% when compared with total withdrawal. Used up by crops, humans, evapotranspiration, and industrial processes. When you open water and it's open to the atmosphere at all temperature, you have evaporation taking place at all temperatures. Okay, even if the temperature is 0 degrees. Of course, the rate of evaporation increases with temperature. This we are going to explain later. And then you have transpiration, which is the loss of water by plants through tiny openings called stomata. Okay, this will also explain in the next chapter very well. So this water, they got lost and they they move to the atmosphere and they get condensed, and then you have rainfall. Okay, so all these contribute to the consumptive uses. Okay, so basically I just explained 3 types of demand here: withdrawal uses, which you use, let's say, for drinking, for irrigation, for water supply, and non-withdrawal uses. And then you have the consumptive uses, which is more or less like losses per se to the system. They could be termed as losses because you cannot have them back again. You cannot get them, you cannot recover them, except, let's say, in this case, for evaporation and transpiration, because they will end up, in the atmosphere, they get condensed, and then they come back as fall as well. But the water that you drink, in which your cells, each cell, you have, if you take biology, you have the cell, you have the cytoplasm, you have this. Our body itself is made up of about 70% water. Our body is made up of 70% water. So our body cells need water to survive. Okay? So such the amount of water that you cannot give it or return back to the environment, then they are termed as the consumptive uses of water. Okay? Now, this is a figure 1.1, which is about water requirements of a city of 150,000 population. Hafrul I don't know how much is the population of Hafrul, but probably, I don't know if it's up to maybe 300,000. I don't know. Okay, let's say around 300,000. So here in this figure, you have well filled 1 million. Woo! So Hafrul is a big city. Okay,
Yes, Doctor, 1 million.
1 million. Woo! So it is really a big city. But I tell you, 6 years back, it wasn't 1 million, maybe 600,000 or thereabout. It is growing by the day. Every now and then, it is, expanding and a lot of development, I tell you. So here you have a well field, okay, and you have a river flowing. So part of water from the well and part from the river are supplying this city, okay, at which rate? 35 CFS. CFS is cubic feet per second. Cubic feet per second, okay? So out of this 35, the household use 40%, commercial 13%, small industries 30%, and public and losses 17%. Losses, you always have losses in the system. I mean, like pipe leakages and what have you, okay? And then the sewage treatment plant, you have a sewage treatment plant here, and the outflow from the sewage treatment plant is 30. The inflow is 35. The outflow is what? 30. So, inflow is higher because you have different uses. You have consumptive use. The difference here, you can say maybe maybe due to the consumptive use, okay? Like here, for industrial use, you need more water. You can see the flow rate double, it doubles that of the municipal water supply. This is 70 cubic feet per second. For large industries, they use, large volumes of water. So large industrial use, this is industrial waste treatment. And then the outflow from the industrial waste treatment is 63 cubic feet per second. So here the consumptive use, could be, the inflow minus the outflow, okay, which is 7 cubic feet per second, isn't it? Okay, and then here for thermal power plant, they also use huge amount of water for thermal power plant, because normally they use water, they vaporize it, and then they use it in generation of electricity. Okay, they use steam. So they use steam boilers. Okay, water is converted to steam, and then the energy in the water is now used to run the steam boilers. Okay, so here you have 150 going in and 149 coming out. Okay, and this is the river flow rate. At this point, this is the flow rate 1055. This is 1042, which has reduced because of the extraction, the withdrawal, okay? And then, unfortunately, due to consumptive uses, it's not the same inflow. There is difference in inflow and outflow. So that is what is making the flow rate here less than the flow rate at this point, okay? And here, waste dilution, about 800 cubic feet per second, okay? So now, get your pen and paper. I will ask you a question now. Now, concept quiz. Very simple question. From figure 1.1, the municipal consumptive use is, you have A, B, C, D. So now tell me, what is the municipal consumptive use? Okay, A, B, C, and D. So type your answer. Type your answer. Municipal consumptive use. Can you hear me?
Yes, Doctor, yes.
Yeah, so what is the answer? Okay, type your answers, all of you. I want to see your answers for all of you. Ahmed, Abud. What about the remaining guys? I saw Ziad saying B. I don't know how he gets B. Okay. Yeah. In minus out. What entered is 35. Okay. What entered is 35. What went out is what? 30. So inflow 35, outflow 30. 35 by 35. So our answer, the correct answer is D, isn't it? Now, oh, this is not showing correctly. Municipal requirements. Okay, here municipal requirements. By municipal here we mean township. Okay, a town. Is that clear? You know half about the municipality. Okay, yeah, this one. Okay, this is saying municipal requirements. I can just write it. I can just write municipal requirements depend on municipal requirements depend on. Okay, so the first here is population, and then population characteristics, and then nature and size of industries, and then climatic conditions. It will be clear on the slides when I upload it on Blackboard. Okay, and then cost of supply. Okay, so municipal requirements, you know, for supply of water, okay, depends on the population. Of course, population is one of the most important factor here. You need to know the population size that you want to supply water to, and then the population characteristics. The population characteristics here may refer to, I mean, how are they increasing? Okay, I mean, is the population the same or are they reducing? You may have some towns whose population is reducing. Okay, and then nature and size of industry. Do you have huge industries, you know, large industries that demand a lot of water, or is it that you don't have any industry? Okay, and climatic conditions here, you know, is it, you know, the weather, is it like a country in which you have, I mean, it is very hot, you know, in hot weather definitely you need more water than in cold weather. Okay, some countries are just perpetually hot, okay, or having, you know, mix between, or halfway hot and then, you know, half of the year cold. But you have countries in which, I mean, throughout the year it is cold. I mean, the highest temperature may just be like 20 something or 30 something, which is really small. You can imagine in Saudi Arabia the highest temperature reaching about 50 degrees in the summer. Okay, and then cost of supply. I mentioned about desalination. Water treatment using desalination is very costly, very costly. Okay, so only rich countries can, you know, really afford using such technology because it is very costly. Okay, treating water using desalination. Okay, while there are other cheaper methods like I told you, you have groundwater as well. Like Haffelbathing is currently supplied by about 14 wells, about 100 kilometers on Riyadh Road. These 14 wells, they pump water to the treatment plant. You know, they pump water to the treatment plant, and the treatment plant, you know, treats the water using basic treatment techniques, and then they pump it to the municipal areas. Okay, although you have other areas, maybe it's hotels or buildings that have their own boreholes. Okay, but again, they are also intending to supply, to augment, to stop supplying using the groundwater alone. They want to use also the desalinated water, because to reduce the pressure on groundwater. Okay, so the required quantity of water needed is simply given by the population at the end of design period times the per capita usage. So it is in volume. So the required quantity is in volume. That is L to the power of 3. So the population at the end of design period and the per capita usage. Okay, design period is the period within which or during which the structure is expected to serve its intended purpose. Okay, like for instance, you design water supply for a town, for a population that will grow after 10 years to become, let's say, 10 million. So you design the water for that 10 million. Because after that 10 years, the population will exceed 10 million, and then the existing water capacity will be overstretched. It will not meet the water demand of the community. Okay, so that is the period of the design. That is the period within which the structure is expected to serve its intended purpose. Okay, you have design period being used also for other facilities like roads also have design period. Probably you have seen roads being removed while they have even no pothole, because the design period has been reached. You don't wait until it develops potholes, cracks here and there before you remove it. All buildings, all structures, they have their design periods. Okay. Oh, this one also is not showing population forecasting methods. Okay. Population forecasting methods. Here you have graphical, you have mathematical, you have ratio and correlation, and you have component. Okay, population forecasting method. So I will just give you like 5 minutes break. Just drink water, relax, and then we'll come back. Okay, this is 12:03, so we'll come back 12:08. Okay, so just take break, take water, relax, and then after 5 minutes, we will continue on population forecasting. Okay. Okay, are you guys back? Hello? Hello? Okay, all right. So now, you see, we have been explaining about water resources development. That is the whole process of supplying water to a community from the beginning. Okay, you will agree with me that the first and one of the most important aspect is knowing the number of persons in that community. That is the population. Okay, how many people are residing in that area. From there, you can estimate their demand and then go and look at the available sources that can meet with that demand. So the first thing we do, okay, and it's not just the number of persons available at that point in time, because population, more often than not, keeps on increasing with time. Okay, you just told me that Hafrelbaden is 1 million. I told you definitely like 6 years back, 2014, it is not 1 million, maybe around 600,000. So the population keeps on increasing because, of course, you have birth rates and you have mortalities, but usually you have the birth rates, outnumbering the mortalities. So effectively, you have a positive increase in the population. Okay, so one needs to be able to project, okay, that, okay, now, about in 2020, the population is 21 million. If I want to design a water resources, a water development plan for Hafrelbaden, I want to supply Hafrelbaden with water. I should not use the 1 million that is currently obtainable now. Okay, I need to project, okay, what will the population be in 10 years, in 20 years, in 30 years? Okay, so that is the design period. So I have to choose my design period. Let's say 20 years. Okay, so that way my population forecasting is the first thing to do. Meaning, let's say I want to design water supply for Hafrelbaden for the next 20 years. So currently it's 1 million. So in 20 years, what will the population be? Okay, in 20 years, that is the population forecasting. Is that clear? That is trying to project population projection, population estimation, population forecasting. Okay, trying to forecast into the future. Okay, and there are many methods. The first one, you have the graphical method, the mathematical methods, and the ratio and correlation method, and the component method. Okay, and there are two types of population predictions. You have the short term, which is between 1 and 10 years, and you have the long term forecasting, which is between 10 and 50 years. Okay, so all this is what we are going to learn here about the population forecasting. Okay, so we will learn some of the basic methods that are used for the forecasting. Okay, so let me, yeah, so we will learn some of the methods that are used in the forecasting, and then we will learn, we will take some examples, okay, on how to forecast or how to project. Okay, now short-term estimates. For short-term estimates, 1 to 10 years, okay, you have many methods under them. This is the population curve, okay, population versus time in years, okay. From A to B, here you have the geometric growth, okay, in which the rate of population increase is directly proportional to the percentage of the population that is currently obtainable. Okay, so dPdt is proportional to P. That the rate of population increase is proportional to the population. Okay, and then you have B to C. Okay, from B to C, here you have what is called the arithmetic growth. Okay, in the arithmetic growth, here you have what is called the constant growth, or the rate of population increase is constant, so it's proportional to 1. So the population increase the population is increasing at a constant rate in this case, and that is why it is proportional to 1. 1 here, it can be just be a number, you know, it can just be proportional to k, okay, where k is a constant. And then you have C to D, which is the declining rate of growth. In this case, the rate of population growth is proportional to the difference between a saturation population and the initial population, which is P sat minus P. Okay. For our own discussion here, we will take examples of the geometric growth and the arithmetic growth. Okay, as well as the graphical methods. So, next two, okay. Can you arrow? So, Muhammad, what do you mean by can you arrow? Arrow what? Use arrow. Use arrow where? To show what? Talk. I can hear you. I have enabled your mic. So can I use arrow? I'm you.
When you explain, Doctor,
Okay.
I prefer you use the mouse.
Can you see my mouse pointer? Can you see my mouse pointer?
No, Doctor.
Yeah, but I'm cycling. I'm using the pen to cycle, you know, some specific. Now, can you see me cycling this?
Yes.
Okay, so, and this one. Can you see it? Okay. All right. So let's move to the next slide. Now, for the arithmetic method, like I said, the rate of growth as it is proportional, is a constant. Okay. The rate of growth of the population is proportional to 1. Okay, so when you remove the proportionality sign, you introduce a constant. So this constant Ka, okay, that is the A is indicating the arithmetic growth, where P is the population T time in years, and Ka is the uniform growth rate. Okay, is the uniform growth rate constant. Okay, that is the rate at which the population is increasing. And when you integrate this, of course, when you have this is dP equal Ka dt. Okay, from your math 102, you integrate, isn't it? When you integrate here, this becomes, you know, P over from P1 to P2. Okay, and then so this becomes P. This is P1 to P2, and then this constant Ka, and then T from, you can say 0 to delta T. Okay, and then when you apply the limit of integration, okay, if you call this P1, P naught, okay, so here you will have P1 minus P naught to be equal to Ka into delta T, okay, and then you have P1 to be equal to P naught plus Ka delta T, okay. So meaning this is the initial population P naught, and this is the final population. Simple, okay. So P, you can use P1, P2, you can use P naught, P1, you can use P naught, PT, like in this case, okay. Here I use PT, okay. So it's all the same thing, okay. And we got this from integrating this one. Very simple and direct. So integrating the equation, we have PT equals P naught plus KAT. Okay, where PT is the projected population, T in years after P naught. Okay, is the projected population, T in years after P naught. Okay, where P naught is the present population and T is the period of projection. Here, if you make Ka the sort of the formula from this, okay, just make Ka the sort of the formula, you will arrive at this formula. Okay, so Ka is equal to P2 minus P1 over delta T. Okay, because that is the first thing you need to do. You need to determine the uniform growth rate constant. It is when you determine the uniform growth rate constant that you can now find the projected population. Okay, we are going to solve some examples. Now, this is for the arithmetic method. Okay, for the geometric growth method, we have shown from the graph that the rate of increase or the rate of change of the population is directly proportional to the current population. So when you remove the proportionality sign, you introduce a constant Kp, okay, which is the population growth constant for the geometric method. Okay, and when you integrate, okay, similar to what we did before, you will arrive at this. Okay, you will arrive at this, and from here, when you make Kp the sort of the formula, you will get this formula. Okay, so Kp here is also the uniform, the geometric growth rate constant. Okay, and the unit is per year time. Time here is normally in years. Okay, we are going to solve examples where we will apply these equations. Okay. Yeah, so let me move on. Okay, so in the example here, get your pen and paper, please. From the following census data, estimate the 1995 and 2010 population by A, the graphical method, and B, the most appropriate mathematical method. Okay, so here you have the years 1970, 80, 90, and 2000, population in thousands. So meaning 25 here is 25,000, 30.5, 37.25, 45.5. So we are to, this is the census. Census is counting, no population. Okay, it's called census. Okay, so we have to estimate the population for 1995. 1995 lies between 1980 and 95, isn't it? So this is where 1995 will be, correct? And then 2010. So 2010 after 2000. So 2010 is going to be here, correct? So let's see how we do that. First, using the graphical method, and two, using the most appropriate mathematical method. So all the arithmetic method, the geometric method, they are all mathematical methods. Now, simply plotting this in Excel, which for you did, I mean, you are all conversant with computer. You may not learn Excel probably on your own. You might have learned Excel, but if you don't worry. For numerical methods, CE 301, you will learn Excel, okay? And there you will learn how to plot, how to find the line of best fit, okay? This is just simply plotting this against the year as X on the X-axis and the population on Y-axis, okay? So Excel, it will easily do that. Of course, if you want to do it using a graph sheet, you can do that. You will arrive at the same thing. But then Excel will give you the equation of the line. It will fit. You select, straight line. You can see and then it gives you the equation and the fit. This is called coefficient of determination. That is how well the data fits a linear trend. This is a linear trend, okay? So the highest value is 1, so 0.9919. So it means it is almost perfectly linear, okay? And this is the equation of this line. This is the equation, y equals 0. This x minus this, okay? So to use the graphical method to estimate the 1995 population, 1995 is within the line, so we can easily check, this is 95. Okay, we go up and then we go this way. Okay, which is almost around it gives around 41.3. Okay, thereabout. So that is how we got this. Or you can simply plug in the value of x to be 1995 here. Okay, use this equation, y equal this, okay, and use the value of x to be 95. Okay, and then in 2010, what is the population? You have the equation generated already, so plug x equal to 2010 and you will arrive at this. Okay, very simple and straightforward. Okay, so this is the graphical method. Now the other method, because it says the most appropriate mathematical method. Okay, the most appropriate mathematical method. So here you may choose to use either the arithmetic method or the geometric method. Okay, usually you will realize for a given problem they may not differ so much. Okay, the two may not differ so much, but for the sake of, for demonstration, let me use the arithmetic method here. For the arithmetic method, we mentioned that we first have to determine the constant rate of the population growth, the growth rate constant, Ka, which is given by P2 minus P1. This we derive the formula, isn't it, over delta T, correct? And if we plug in the values, P2 here, it will be for 1995. So we will take the values of population from 1990 to the year 2000. And what is the population? What are the values? Okay, let me go back to my table. Okay, for 1980 is 30.5 minus for 2000 is 45.5 over the difference in the year 2000 minus 1990, which is 10 years. Okay, so what is Ka? Let's do it together, please. Tell me what is Ka now. Oh, no, sorry. It's supposed to be the other way around, 45 P2 minus P1, sorry. So it should be, okay. So it should be Ka equal 45.5 minus 30.25 over 10. Okay, and what is this? You see, that is why I said you must get your pen, because we'll be having a lot of this. Okay, over 10. So this is 1.525. Okay, but this is times 1000. Don't forget the population is in thousand, so this is times 1000. Okay, so the 1 2 so this is now 1525. Okay, and then now to get the population at 95, P 1995 is going to be P 1990 plus Ka, isn't it? T. Okay, and what is P 1990? P 1990 is 30.25 times 10 to the power of 3 plus Ka, which is 1525 times T now is 5, isn't it? Because it's from 1990 to 95. Okay, so let's So this gives me 37,875. Yes. Okay. So this is the population for 1995. Okay. And if you like, you can use the geometric method as well to check. It may differ slightly with this. Okay. The value may differ slightly. Y5. Okay. Oh, I hope. Y5, because from 1990 to 95, that is 95 minus 1990, which is 5. Okay, it is the time. All right. Now, attention quiz. You have to solve this and let me know your answers. From the census data provided in example 1, which is this one, this table produced, estimate the 1985 now, not 1990. Estimate the 1985 population by arithmetic growth method. Okay, here I'm specific. I asked you to use the arithmetic growth method. Hint: find the population growth constant Ka using 1980 and 1990 populations. Okay, so solve it and let me know your answers. You have 2 minutes. Okay, 2 minutes. Just post your answer A, B, C, or D. Okay, you have 2 minutes. Yes, I'm still waiting. Only one person posted his answer. Work it out. Let me know your answers, please. Yes, yes, yes. You are taking longer than necessary. Post your answers. I'm waiting. Two guys are absent today. I have 12 in the class. Post your answers. Okay, it seems okay. You're all getting C. Okay, so I think the correct answer here is C, which is also very simple. Okay, you get your Ka, isn't it? By subtracting, isn't it? P2 minus P1 over T, and then you now substitute. Pt equal P naught plus Ka times T. Okay, and you will arrive at this. Very simple. Okay, now let's move on. Now this says a city has a present population of 200 200,000, okay, which is estimated to increase geometrically to 220,000 in the next 15 years. The existing treatment plant is 51 million gallons per day. MGD is million gallons per day. Okay, MGD, million gallons per day. The rate of input to the treatment plant. So the capacity of the treatment plant is this, the existing, that is the current capacity. The rate of input to the treatment plant is 165 gallons per person per day. For how many years from now will the treatment plant be adequate? Okay, let me break down the question so that we understand. We have a population now of 200,000, which will increase to 220 geometrically in 15 years. Okay, in 15 years, it will increase to this number. The current capacity of the plant is 1 million gallons per day. And then the rate of input to the treatment plant is 165 gallons per person per day. Gallons per person, or you can say per capita per day. Okay, gallons per capita. Capita is person. Okay, that is per head. So the current input is 165 gallons per capita per day. So now, if we want to determine the population now that it can serve, okay, the first thing that we need to do is to try to find the population that can be served by the plant, okay, based on these two numbers. This is the plant capacity, and this is the input per capita per head, okay, per day. Okay, and how do we do that? By just dividing. This is in million, isn't it? Okay, this is in gallons per day. Okay, and this is 165 gallons per head. Per head meaning that is the population. Okay, gallons per capita per day. Okay, so now gallons cancelled, day cancelled. So capita now will now give us the population. Okay, so this total we will get about 309 persons. Okay, what is the capita? Okay, 309 persons. Okay, so the plant capacity will be able to serve this number. Remember, the population, current population is 200,000, and it will increase to 220 geometrically in 15 years. So the question is saying, how many years from now will treatment plant be adequate? You can see that the treatment plant is currently, it can serve up to 309 persons, but it is currently serving just 200. So how many years will it be adequate? So we will use our geometric progression, isn't it? Because it says it geometrically, isn't it? It increased geometrically. Okay, this is mentioned clearly here. So first we need to find our K as usual, isn't it? Yeah, correct. We need to find our K using the geometric progression, okay, which is KP. Okay, okay, so we use ln P2 minus ln P1, okay, over 15. Okay, so this, there is ln here, please. Okay, there is ln. Okay, yeah, there is ln here. Okay, ln P2 minus ln P1 over T, which is 15 years. Okay, and then the population that can be served by the plant, we got it to be this. Okay, now time to reach the desired population. Now we want to find the T, isn't it? Remember, ln PT is equal to ln P naught plus KPT. So we want to find this T. We know KP, we know P naught, we know PT. Okay, PT now is not 220. Okay, it is the number of persons that the plant will be able to serve. Okay, which is 309. Okay, and this is the initial population. Okay, and this is T that we are looking for. So the plant will be able to serve, or it will be sufficient up to about 69 years. Okay, because just imagine the population increases from for just about 20,000 in 15 years. In 15 years, okay? So this way are talking about 109 increment, okay? So that will happen, you know, it will be sufficient up to about 69 years. Is it clear? Oh, my time is up. I will stop here till next week. Like I told you, next week our practical class is going to begin, and it is going to be in the class, okay? So you need to be here, okay? And then you need to be here kitted, you know, in your practical ways, and then we begin the practical class next week, okay? Any question? Yeah, I will upload it right away. I will upload this chapter, I mean, up to where we stopped here, I mean, we upload it right now, okay, on the blackboard. All right. All right, see you next week. Thank you too. Bye-bye.
Doctor.
Yes.
Doctor, I have a question, Doctor. You are my advisor.
What?
You are my advisor, Doctor. I
Okay.
have a problem.
Okay.